Hello everyone. Thank you very much for having me here. Let me make a confession here. Do you understand correctly that I'm the only STEM person in this room? STEM means for science, technology, engineering. Okay, yeah, thank you very much. Thank you for your support. Thank you for your support. Yeah, so let me get started. As you can see, my topic is making dynamics dynamic. Interactive, computable lecture presentations for STEM. So, briefly about me, right? So, I'm from, since 2007, I guess, I teach in academia and I deliver STEM courses, as you understood. It is, for example, classical and applied mechanics, spaceflight dynamics, applied mathematics, other things. And I used to work in industry for 7 years, building mathematical models for helicopters, so I do know how to apply this theoretical knowledge. And my research interests are space junk removal and many other technical things. Currently, I'm managing a project administrator grant on this topic. All right, so to interactive computation and to interactive presentation. So let me start right away with this empty slide. Okay, so let me do the following. Let me just type 2 plus 2 here and press a button. You can see, turns out it is a 4, right? So I can do more. For example, I don't know, let me do a simple algebra here. How about 10a minus 2a? So the answer should be 8a, and it is. So as you can see here, I'm presenting, it's not a PowerPoint, it's not a PPT file, it's just something which is alive. And that is what I do in each of my lectures. How do I do this? So how can I do this? Of course, I need a special tool, and this tool is called Wolfram, right? So formerly Wolfram Mathematica. So that's a computational system, actually. So, and it's also a programming language which is designed for symbolic mathematics, numerical computation, algorithmic modeling. So you can think about this as a programming language. That's it. It just has a nice interface. And the thing is that, as you can see here, coding is unavoidable if you teach and if you learn STEM and if you do STEM. It's just it's no more question. Yeah? You cannot do without coding. So that is why in our school we teach Wolfram starting from the 2nd grade. It's a core course. It is called Engineering Mathematics, right? And we have 5 sections for this course. So almost everybody in SEDS must take this course. Okay, so we're trying to reach, large audiences here, and the key features of this Wolfram piece of software is symbolic mathematical operations, and let me say that is quite rare. For example, in your mind immediately things like MATLAB or Python pops up, right? But this is rare, and I will show you this in action. Numerical computations, that's pretty common. Every computer programming language can do that for you, and I will demonstrate it. That's pretty easy. And now another very funny feature which Mathematica has, it is native interactivity, natural interactivity, easily accessible. And I must say that this thing, even in 2026, is pretty rare. Okay, so, and the thing is that my bottom line here is that I try to fuse all these 3 features together in each of my lectures. All right, so let me show you this slide here. I'm particularly proud of this one. So that's a screenshot from my computer, right? My 91 interactive computable presentations, and that is just for fall 25, spring 26. If you think about how many versions of this, so it's my 3rd year here at NU, so multiply this number by 3, and then multiply this number by at least 5 hours needed to develop each of these presentations. So I simply would like to say that I know something about it, right, from my own experience, and let me share this experience with you. But before I dive into these STEM topics, by the way, I try to squeeze this STEM content as much as I can. Yeah, I tried my best. Yeah, let me start from this non-STEM teaser. So look at this. It's a history timeline. By the way, I'm not a historian. That's not my topic. So maybe my analogy will appear, I don't know, weak or too simple and everything. Again, I'm trying my best here. So that's just one timeline. And it has something to do with, you see, Russian or former Soviet Union history. You have this assassination in Sarajevo, you have Russian Revolution, you have World War II, and you have World War II ended. And in a typical textbook, it looks like this. You just see the story, you see the timeline, and that's pretty much it, right? Okay, I'm generalizing here, I'm oversimplifying here, but you got my point. The problem is that causality, this reason and the consequence, sometimes they're hidden, right? And you do not know the answer to the simple question, what if something went different? And now imagine the same timeline, and look at this. Change this event. For example, everybody knows that the Russian Revolution in 1917, it was a pretty complicated process, and there was a lot of, random things going there, and let's just imagine that it didn't happen, right? So that would lead to different alliances, different war alliances, military alliances in 1940. Okay, maybe that would change completely the history, right? But of course, everybody knows that history doesn't tolerate that. In history, you do not have this thing which is called subjective mood, right? But STEM teaching is completely different. In STEM teaching, we cannot live without this very simple question: what if? All right, so now let me get from this non-STEM teaser to a STEM teaser. Look at this. So you're looking at a typical picture from a textbook. By the way, that's a very good, famous textbook by Craig Clever called Spaceflight Dynamics. And what you see here, it is a spacecraft which is changing its orbit. So originally, it starts in orbit near Earth, and then it burns some fuel, turns on his engines, right, and just it moves to another orbit. All right, so that's the problem with this picture. Again, it's kind of static, right? Because you do not see any causality here. You cannot ask the question, what if? What if my thrust, well, that means the force that I'm applying is larger? What if this force is smaller, right? And now compare this to that. Look at this. That is the same thing, okay? You see the Earth, you see the initial orbit, and you see the orbit, the distance that you would like to reach. And now, let me just click this play button, and now you can see this spiral evolving. So the spacecraft is burning its fuel, accelerating, and it leads to this rise of the orbit. And needless to say that, as you can see here, okay, so I can stop it at any point. I can discuss any number here with my students. For example, so sometimes I say, look guys, look at, focus on this number. Look only on that. Okay, let me run your animation for you once more. Look how this number evolves. Try to think, why is that, right? And so on and so forth. Look at some magical points. That's the periapsis, the closest point to the planet. That's the apoapsis, the farthest point, and so on and so forth. And as you can see, this thing is alive. And maybe you're asking yourself, what is this magical number 100 here? And let me tell you this. That is the thrust. That's the amount of force that I'm applying. And turns out it is this 100 is just something like 10 kilograms. Very weak force. But let me do this. Let me switch to 100 kilograms force. Now, look at this. I'm burning my fuel, but now I'm not spiraling anymore. The orbit changes, and again, I'm reaching this high orbit that I would like to reach, but I'm doing it in a much more effective and faster manner, right? Again, so that is my answer to the question, what if? What if my thrust is larger? That is the answer. You can immediately test it. And I can increase the thrust even more, right? And show you something which looks like that. All right? So as you can see, I'm burning fuel, and I'm extending my orbit, and I'm still, look at my actual trajectory, I'm still near the Earth. And you know what? That's exactly how this famous Artemis 2, that is how they departed to the moon, right? So to go to the moon, you reach the orbit near the Earth, then you burn your fuel, then your orbit reaches this point, and now something cool happens. You turn your engines off. and just gravity is driving you through the space. And we always say in mechanics that we are driven by Sir Isaac Newton, right? Because that was the guy who discovered this, right? Sir Isaac Newton is our god in mechanics. All right, so that was this interactive demo. Here, and hopefully I succeed to demonstrate this causality, right? So the answer to the question, what if? But the thing is that in teaching STEM, that's just only one aspect, okay? There are a lot of more. So in practice, we have a larger problem. And this larger problem, as you can see, is that we need to master the whole sequence of something called a mathematical model. Okay, let me repeat this. We need to master the whole life sequence of a mathematical model. So I guess I need to explain, or at least to remind, what mathematical model is, right? So mathematical model is just the way, first of all, the core concept of all STEM courses, right? Of all STEM disciplines. It's a way to describe the behavior of a system. It can be anything. It can be your engine. It can be your spacecraft. It can be, I don't know, even some population in biology, right? You can describe with a mathematical model, if I'm not mistaken. So, and the power of mathematical models is that we can predict things, right? So that's why sometimes I distrust people who says, okay, I know what's going to happen. And I'm asking, do you have a mathematical model, right? Because I'm kind of biased. In mechanics, in STEM courses, we do have these models, and they really work. They can predict. And a typical mathematical model, sorry for that, but it looks like that. It's just a crazy set of equations, for example, like this. So these equations, by the way, they describe the famous three-body problem. There is a book, yeah. Okay, so three-body problem looks like that. Okay, so now let me tell you about the life sequence. It's not a life cycle, right? Rather a life sequence of a mathematical model. The challenges that students face and my solutions that I suggest. So first of all, let me start with the challenges. The challenges, three challenges here, they are on the left. So first challenge is derivation of equations, right? So unfortunately, for example, in spaceflight dynamics, not all equations, they are already pre-derived for you. You need to hard work, okay, so here is my new problem statement, and I do not have this in textbook. I need to derive it myself. I need to do this algebra, I need to do this calculus, integration, crazy things. And that's pretty complicated. Challenge number 2, numerical simulation, right? So if you have your equations, you need to run them. You need to use them to actually compute something, and sometimes it is quite challenging, especially if your equations are complicated. And last but not least, visualization and analysis of results. We need to, because I always say to my students, if you do not have a plot, you do not have understanding. You need to plot things. And now look at this, the challenges. First of all, overwhelming algebra, I already mentioned that. If you derive something, calculus and algebra can be complicated, especially if it is not a just learning problem, if it is a real-world problem. That's quite a challenge. Numerical simulations, what I face all the time, and I will discuss today, students, sometimes they have a considerable lack of coding experience. And the problem, for example, with textbooks is that sometimes they do provide some codes that you can try, but again, you need to retype them, right, something like that. And sometimes they are just completely missing from textbooks, but that is needed. As I said, we cannot live in STEM without coding anymore. And the last challenge is that I already showed you, static plots, they kind of hide causality from us. We would like to see system evolve dynamically. And those are my solutions. I will show you that derivation of equations, even this complicated algebra, maybe you remember some equations, manipulations, some parentheses, some factorizations from your high school days, right? You can use computer for that. Numerical simulations. I include all the codes that I need to simulate stuff in my presentations. They're directly accessible to my students. And my famous part, as you see, it is interactive dynamic plots. I can immediately visualize things. And of course, all those solutions here, they are kind of stored in a single file, which is called my presentation file, which I share with my students every time, after every lecture. Okay, so now let me show you the first part. The first part, remember, is the scariest slide ever. right? So that is the symbolic derivation of equations, orbital motion of spacecraft. So that is how it looks in the textbook. We have a couple of bodies, the gravitationally attracted. All right, we introduce some coordinate system. We need to derive it. So let me show you that all this in the textbook, it takes 2 or 3 pages. Sometimes, for example, that's an excellent textbook, by the way, this textbook by Curtis. But I noticed that sometimes the equations, they just contain typos. Just imagine this. It's the best spaceflight dynamics textbook. It contains typos. And what I'm doing in my lecture, I'm rederiving these equations symbolically using Wolfram Mathematica just to avoid these mistakes and to show the, a nice workflow. I'm introducing a couple of vectors. I'm calculating the magnitude of this vector. I'm introducing this famous gravitational force derived by Sir Isaac Newton, right? I'm doing all this stuff programmatically, okay? I'm not touching to my pen. I do not touch to my notebook, right? And at the end of the day, let me get to the bottom here. I'm having a system of equations, right? That is my mathematical model. That is the core of my future simulation. All right, but before I dive to the simulation, let me discuss some pedagogic value of this. What is cool pedagogically about symbolic derivation of equations? So first of all, your derivations, they become reproducible and reliable. Every student can open this lecture notes with Mathematica because they know Mathematica, they are taught to use Mathematica, right? They can reproduce those equations and there won't be any mistakes. Right? So if you're okay, you can make mistakes in coding, but no mistakes in algebra. Forget about this, right? No missing pluses, minuses, nothing of this kind. And there is another thing. Every step is computable, right? So you don't need to trust those printed formulas which do contain typos. I know it from my experience, right? You just derive everything by yourself. And last but not least, this is a robust technique that works on any scale. Every of my research papers, which is in spaceflight dynamics, and I do derive equations there, every research paper is made in Mathematica. I mean, the coding, the derivations, they're made in Mathematica only. And so we literally can write one-liners, right, for simple stuff, and we can do research papers. And down there you see an example of a pretty complicated space tether system that we studied in my research project. And that is my PhD student, Arjan, who actually derived those complicated equations. And it took 2 days for her to derive it. Just imagine how long would it take if she just do everything manually on paper. All right. So now to the numerical simulation, right? So that's the second step I'm talking is numerical simulation of our mathematical model. So here I'm trying to keep the things simple. So all we need to do is just to run this line of code that I have pre-coded. And as you can see, just raise orbit simulation for 100 Newton thrust. And as you can see, that's what we get. We get a ton of numbers, right? It's even for me, it's pretty non-intuitive. What is this, right? So Mathematica just tells me where my spacecraft is at any moment in time. So generally, it's a huge table of numbers. That's it. So I cannot use this to derive any conclusions or anything of this kind. That is just not enough. That's important, but we need to get to analysis of that. But before we do, let me show you the hidden beauty of this. So behind this code line, raise orbit simulation as a function of thrust, you can immediately recognize, hopefully, the equations that I already showed to you, some parameters of this problem, and some other technical stuff. And the cool part about this technical stuff, that everything can be tuned by my students. After they get this presentation, they can tune, okay, how about we change this radius of apoapsis? How about we change the mass of the spacecraft? That can be totally changed and checked. All right, now to the pedagogical value of all this, right? So this numerical simulation that you just seen, that creates a transparent, very nice and understandable link between the equations, which are pretty abstract, and the actual behavior that they describe. And students see the model, not a black box. I showed you the all inside of this thing. You've seen that, right? You can open it, you can change it, you can run it, and you can see. Okay, you can build, modify, and question. Okay, now to the third part. This part is already familiar to you, visualization and analysis of results. So let us just recall our animations from above. So if we have a small thrust, the spacecraft is spiraling outwards, okay, reaching the orbit in a certain amount of time. If we make our thrust larger, right, the spacecraft reaches the same orbit faster. The motion looks different. It's still a spiral, but you can barely see that now. All right, so everything is breathing, everything is alive, right? And we can immediately make these conclusions. For example, as you can see, I've just made this conclusion right now. So if I have a larger thrust, my trajectory looks different. It's not, it doesn't have so many lines of the spiral. I reach the orbit faster. That's a very simple conclusion, but it's pretty important one, I would say. All right, so to the pedagogical value of this. As you can see, with this technique, I just make students, I just move them from passive method to active method. Students, they test ideas themselves, right? They take my lecture notes, they change something, they test it. And the cool part of that is that they get this feedback, not even from me, right? Because they do it at home. They get this feedback from the software, because software, okay, that is what this thing is gonna look like, right? Immediate feedback from the software. And needless to say, it's not abstract anymore. So those are not just symbols or some dumb equations. Those are concrete results that can be and should be, must be interpreted. Okay, so now let me show you more visualizations. Because as you can see, I'm totally into it. So I cannot help. I must show you at least 5 more visualizations without longer comments. So just look at what we're doing in our lectures. So for example, the first animation is the moon orbiting the Earth. And if you can see, the orbit of the Earth, the orbit of the moon is not purely circular, it's not purely elliptical, it's kind of drifting. And it turns out that that is the sun. That is the sun who's perturbing the motion of the moon. That is why the moon is drifting. Okay, so that's just one example of such a visualization. And of course, behind that is a numerical simulation. You can, I don't know, you can change the mass of the moon, right? You can change the parameters of the orbit of the moon. You can add another moon to our system. What if we have 2 moons? You can totally do that and look at the result. Maybe one of these moons is going to be thrown away from the system. Who knows, right? You can test it. Okay, so, that's one of my favorites. And by the way, guys, I noticed that in this, at least in this section, I'm the only person who doesn't have an AI in my title. Yeah, I was really concerned about that. So let me tell you this. I used AI to create this nice gradient atmosphere around the circle. Right? So, yeah, I'm with you, yeah, because I'm kind of afraid to appear old-fashioned or something. I use the AI here. All right, so the cool part is, look at this. Look at this. That is this satellite in a very elliptical orbit. And look at this. The satellite is passing through the atmosphere and it orbits shrinks. It orbits shrinks because of the air resistance of the atmosphere. That's one of my favorite animations in spaceflight dynamics course. We gradually approaching the Earth initially from being initially far, far away, and it takes just 2 or 3 days. That's the power of the atmosphere, if you're close to it. All right, so another visualization is this, a 3D motion of a fancy shaped satellite, like this. So you can think about something like a badminton shuttlecock. That's the same idea. The wind is coming from some direction and the satellite kind of reorients itself. Okay, and that is, that's about my research project right now. So the ministry grant, the project is called TARAS, by the way. And that's some fancy acronym. I didn't want to decipher this. Let me just show the animation. So we can deploy some deputy satellite on the tether. We can open some panels here, like this. We can open a sail, and then we can deorbit this small bad guy, but this guy is gonna be resistant. This guy is gonna do something like that, but at the end of the day, we'll win. All right, and now the last visualization here. It is something much more abstract. So notice that all my 4 previous visualizations, they were about actual objects moving, right? But now look at this. That is some fancy potential energy of gravitational and dynamic torques, very, very abstract things that we need in spaceflight dynamics, and sometimes we need to see those things, those plots, evolving. And just, I don't know, try to, look at this point here. So look at this, we automatically kind of detecting the hills and the valleys. The valleys are green, hills are red, and if I move the slider, actually I'm changing the altitude of my satellite, I'm going down. Look at the central point, the central red point. Somewhere, oh my goodness, this point just splits into 3, and as you can see, the code automatically detected that it's going to be a valley, there's going to be 2 hills there, so sometimes we need that. Pretty abstract thing. I cannot imagine this showing this evolution without this simple slider that is needed. Otherwise, oh my god, that is complicated. Okay, so 2 bonuses that my students receive from all that. So bonus number 1, as you probably noticed, I was showing you some equations, I was showing you some figures, I was showing you some simulations and visualizations, and I never switched the screen, right? And that's rare, I must say, because typical lecture is, okay, you have your PDF, and you have your MATLAB, you're showing your codes, but not like that, not with Mathematica, not with Wolfram. So it's single window service, and I find it particularly cool. Bonus number 2, let me get to it. Bonus number 2 is live coding. So that is the part that I particularly adore during my lectures. I'm explaining things, and some student just raise their hand and they ask me, okay, what is this? What if I change this? How do you do this? For example, okay, professor is showing us the sinusoid plot, but how can I make it, I don't know, how can I make it red, right? And I'm saying, okay, yeah, you just do it like this. You just type plot style, you say red, okay, how can I do this? Yeah, this is red, okay, there's some suggestions, and there you go. So as you can see, I'm not just explaining, I'm showing it right away. Right away, I can totally do that. I'm making a pause, I'm discussing this, I show it in action. I'm not telling, I'm showing. All right, so, and there's another thing. So, in every of my lectures, my goal is to inspire students to be like me, right? To deliver their research results. It's not necessarily that you always must do this, right? But sometimes it kind of works. And I stimulate them, I encourage them to prepare their own presentations. And here you can see a couple of screenshots from the last year presentations that the guys prepared for the Numerical Techniques for Engineers course. As you can see, taxi travel optimization, suspension parameters of some rail transportation device, airflow analysis, oh my god. And everything can be done with just one piece of software to train their research communication skills. All right, now to the feedback. Okay, so let me be honest with you. I received pretty a lot comments, supportive and complimentary comments in my feedback. So a couple examples are here. So people praise many things about this approach, about my style, about this Wolfram usage, right? So I really like this expression. I didn't know this expression anymore, but turns out that nowadays students, they just love this expression, absolute cinema. I didn't know this before I got last year's feedback. But now look at this. Sometimes I see something like that. It's rare, but I see that. Dear professor, could you please focus more on the algebra and equations instead of the software in the lectures? Yeah, sometimes I get this. And you know, that's quite a challenge for me. And okay, you're thinking, yeah, we are non-STEM people, so we understand we do not have any coding backgrounds. I was like that, I was thinking like that. But this year I have a student from Germany, an exchange student. And this student is a molecular biology student, right? And this guy is one of the best in the cohort. And now that completely blew my mind, because originally I was thinking, all right, so students without any code background, maybe that can be complicated for them, I can understand this, and so on and so forth. But the molecular biology guy, right? So now the thing is, dear audience, so I would like to ask some advices from you, right? So I do not know what to do. 80% of the comments, people praise it. 10% or something like that, people just, maybe we could use traditional slides. I actually downloaded slides from the other professor, they were static, they were better for me, right? So that happens, and I admit it. Okay, so to conclude, in STEM, clarity, in my opinion at least, clarity comes from action. You need to interact with the thing. Only after this you can master the contents, right? And even small interactivity, just one live derivation, one live coding session, or one manipulated model, it can significantly change how students engage with our material. And the thing is that, again, I'm thinking about that students with no or weak coding background, they need special support. And currently I'm thinking about this. I'm thinking about it all the time. How can I make this wonderful approach accessible to more people in my room, in my classes? Again, if I would be really grateful for your suggestions. How can I broaden my audience here? Thank you very much.